Well, it is my pleasure to introduce the first seminar speaker today, Aditi Pandey. Aditi came to work with me about 3.5 years ago and immediately started to work on a very interdisciplinary project with four different colleges, working on producing a 3D printable material out of soils, which was a challenge to say the very least. But it turned out quite well for her in many ways. She got a publication out of it and immediately segued into, for her, a job as an intern at NASA Johnson Space Center. And she'll be talking to you about some of the work that she's been doing there for the last couple of years with a minor interruption due to COVID. But she's done quite well. One of the concerns that people often have about someone who's doing really interdisciplinary work is that they can be a jack of all trades and a master of none, as the saying goes, or a mile wide and an inch deep. That was never my fear with her, particularly. I've seen it with others, but I saw the way that she attacked the various disciplines that she needed to work in: mineralogy, chemistry, engineering, and so on. And she achieved great depth in all of the critical areas. This was sort of reinforced when she successfully defended her dissertation a couple of weeks ago. And even further, 5 days ago, when we received notice that a recent publication of hers that she submitted received very glowing reviews. And not just that it was a publication that's now on its way to being published, but it was in the journal Icarus, which is a planetary sciences journal, indicating for sure that she has absolutely arrived in that particular discipline. So anyway, I could go on and on talking about various things that she's done and so on, but that's not why we're here. So Aditi, floor is yours.
Thank you, Dr. Schwab. That was really, really sweet. Thank you, everyone. Good afternoon and welcome to my presentation today. I will be talking to you about a part of my dissertation. It is titled In Situ Resource Utilization for Soil for Terrestrial and Extraterrestrial Construction. I wanted to give you an overview of my entire PhD research. Our research was basically based on us looking at two very distinct research needs. And both of these needs relate to the applications of terrestrial analog soils. I'll be using the word simulant or analog soils a lot. And I wanted to start by describing to you what that means. Because we haven't had any sample return from Mars, and any of the samples that we have had from the lunar surfaces are very hard to come by. So any application or any research that requires you to test whether your hypothesis, your idea is worth trying in an extraterrestrial surface or not, you'll have to come up with a simulant soil. So by that, we mean soils from these very rare locations on Earth that have similar mineralogical as well as spectral signatures that match what has been observed on extraterrestrial surfaces. So between the two distinct research needs today, because of time, I'll be talking to you about one of them. And it is the design of regolith-based composite materials for sustainable construction based on the ISRU principle. And by ISRU, I mean in situ resource utilization. So let's jump into the rationale itself. In situ resource utilization was a concept that NASA came up with a long time ago. And the idea is to use whatever is existing in the planet in order to reduce cost, in order to reduce contamination of terrestrial materials into extraterrestrial surfaces, and to reduce payload. So just imagine going to Mars itself is already a huge cost-effective ordeal, and to take materials in order to construct anything or to do development in terms of infrastructure is kind of not viable. So the idea is to use whatever materials already present in these surfaces. And so we first start by coming up with these composites by choosing a binder material. And so for that, we've used magnesium oxysulfate cement. Magnesium cement has been identified as an indigenous binder material by NASA itself for their 3D printing habitat challenge competition. And this is because magnesium oxysulfate cement, or magnesium cement in general, at least the major components or the reactants that are required for this cement are indigenous. So it can be produced on Mars itself. And here in this figure, you can see a process for magnesium oxide synthesis from a very common mineral, olivine. So we could do an acid digestion of olivine to create magnesium chloride, which can then be pyrohydrolyzed into periclase, which is the major reactant for magnesium oxysulfate cement. We can also do a supercritical carbonation of olivine to give us magnesite, which can then be calcined to form periclase again. So the idea is, okay, we have identified these processes. Let's see how much olivine is actually present on Martian and lunar surfaces. So the magnesium oxide itself is present in some Martian samples, and it can go up to 9.3% by weight. Olivine, on the other hand, is a lot more abundant. So on Mars, they've identified olivine up to 30% by weight. And in Moon, the soils, they've identified it up to 11% by volume, and in rocks, up to 44% by weight. And in terms of the sulfate component, there's a lot of sulfate moieties that have been identified with the rover analyses. And one of the more famous examples of this is the ancient sedimentary rocks in the Gale crater as analyzed by the Curiosity rover. They've come across a lot of sulfate deposits. So these are mineable. So this makes it exactly what we're looking for. So we're trying to find indigenous materials that we can utilize on the surface itself. So project synopsis, we start by characterizing these materials itself. So we need to be very confident that the materials that we're using is actually representative of what's being observed on Mars or on the Moon. And so in order to optimize simulants on Earth to study what's happening on Mars, we focus on, for this project, we focused on iron-rich basaltic soils because a lot of the samples that they've analyzed, actually pretty much everything that they've analyzed on Mars and Moon are basaltic in nature. So we focus on iron-rich basalts with various degrees of alteration and various degrees of secondary alteration products. So because basalt itself is not very reactive, when it does go through alteration, we create a lot of secondary alteration products that are reactive, such as amorphous phases. And these phases can help us with our reaction. They will react with our binder agent, which we'll see shortly. And so in terms of how we were going to go about doing this, we decided to take the idea of biomimicry. This has been a concept that's closer to heart for me. I first watched a TED talk on biomimicry, I think when I was in high school, and it really, really like stunned me. And so we came up with the same concept. Okay, they've already found consolidated rocks, mudstones, sedimentary rocks that seem to withstand the environmental conditions under which we are talking about constructing. And so why not design materials that follow the same design? Like, why wouldn't we come up with materials that would pretty much mimic what's already on these surfaces? And so with that in mind, and combining that with historical construction techniques like adobe rocks, which is mostly made out of very high clay soils, we came up with the same concept. So we developed materials with close chemical and physical resemblance to well-consolidated outcrops that are already resilient, and they've proved themselves to be resilient against the environmental factors at which they have to sustain. So let's move into materials and methods. We start by looking at these simulants. So for this part of our research, we acquired 4 different simulants from JSC. The first 2 are the Mars simulants, and the second 2 are the lunar simulants. So the Mojave Mars simulant is one of the more famous ones, and it is made from crushed basalt that was extracted from the Saddleback basaltic flow in Mojave Desert. The GSC Mars 1 is no longer available in the market. A lot of these samples, actually, we were very lucky to have whatever minimal amounts that were left back in the GSC labs. And it is made out of volcanic ash in Mauna Kea volcano. So as you know, Hawaii has very high strict restrictions about any excavation or any sample being collected from the islands anymore. So this sample is pretty much no longer available. The Minnesota lunar sample, lunar simulant, which is a crushed basalt from a quarry in Duluth in Minnesota. And then the JSC 1A lunar simulant, which is a volcanic ash that was extracted from San Francisco volcano in Arizona. When you look at the second point in all my simulants, they pretty much tell you what you would expect from basaltic soil. So it is composed of a lot of your typical basaltic minerals, including your plagioclase, feldspars, pyroxenes, and olivines. And definitely because they're volcanic in nature, there's a lot of amorphous materials in these samples, and there's some magnetic features as well. So just finding a basalt doesn't always give you the answer, because basalt on Earth is more silica rich than iron rich. There have been a lot of excavations and expeditions to try and find basalts that are actually high in iron content. So let's move on to the binder itself. The magnesium oxysulfate cement is a pretty straightforward reaction. We react magnesium oxide with a magnesium sulfate solution, and depending on the temperature at which you're reacting these two materials and the molar concentration of magnesium to sulfate, we can come up with various phases. It is a solid solution that is a hydrated phase. And so you can come up with all sorts of different compositions. But our target has been the 318 and the 51N phases. These are known through literature that they have much higher hardening properties. They have high mechanical strength. And so in order to approach this whole consolidated soil sample, we decided to add 12% by weight magnesium oxysulfate components to our simulants. And then we add just the right amount of water. So you don't want your sample to be too mushy. You don't want to have a very dry sample. We call this an optimum moisture level to which you can get maximum density. So the water level corresponds with overcoming any friction that is between particles. So when you compact it, you're getting the maximum density you can from a mixture. So sample preparation. As I mentioned several times already, our major problem, like one of the biggest hurdles that we had to face for this project, was simply the lack of enough simulant. If you've ever been to a civil engineering lab, they make massive columns. Their sample sizes are huge, like 2 inches by 4. That's like a standard. Whereas for us, there is no way we had enough materials to make such large samples. So we went with undersized columns, and I mean tiny. We were making columns that were 15 millimeters in diameter and 18 millimeters in height. You can see just how small they were from these images. And in order to mimic the environmental conditions, it was stressful, but we made these samples from scratch in a walk-in refrigerator at 4 degrees Celsius. I was wearing gloves, caps, boots, but I was in there. And then we cured them in a desiccator that I placed inside this refrigerator in order to maintain, because I don't know if you've been inside refrigerators, they are very high in humidity. So we wanted to make sure our humidity levels were also controlled. And so we used a desiccator in order to give us about 26% relative humidity. And for testing, we took our samples to CIR at Tamil. I don't know if you've been there at the Relis campus. We used the Instron universal testing machine for our unconfined compressive strength test. Basically, it is a uniaxial force test. So you just have this huge frame that's constantly putting pressure on your sample, and you're trying to see when it breaks. When it breaks, it means it has gone through plastic deformation. So we're trying to find out what the maximum amount of force is that takes to break our samples. And then after it breaks, I collect whatever little pieces are left, and then I sieve them. I try to get the finest particles I can, and then we look at these particles under the scanning electron microscope in order to see any morphological differences. And so for this, we use the FEI Quanta 600 field emission SEM at MIC, and it has an electron dispersive spectroscopy capacity as well. Let's move on straight into the results. For results, I have sort of organized my results by hypotheses. So I'll give you my hypothesis and then I'll show you my results. So our first hypothesis for this research was that magnesium oxysulfate cement enhancement of mechanical properties of the simulants will be comparable to traditional stabilizers. So traditionally on Earth, there's a lot of stabilized soils that are being applied for all sorts of things. Before you build upon a structure, you usually want to stabilize the soil. So for that, the most commonly used material is lime, but sometimes they use Portland cement. And for our purposes, I've put in some data for Portland cement. So let's look at our compressive strength. In y-axis, we have the compressive strength in megapascals. The first 2 bars in somewhat orange brown is representing our stabilized marsh simulants. The two gray bars right after that are the stabilized lunar simulants, and then the red bars are, data from the literature about Portland cement stabilized soils at 10% by weight and 30% by weight. So first thing we noticed, we definitely saw some strength improvement. And some of the strength improvement for the Mars samples compare pretty well with the 10% Portland cement stabilized soils. Whereas for the lunar samples, we saw some pretty incredible increase in strength. So these compare better to the 30% Portland cement stabilized soils. And we wanted to investigate further why it was so. So with our SEM images, we sort of come to that conclusion. So our second hypothesis was that interactions between the major products of the magnesium oxysulfate cement and the reactive phases in the simulants will occur. So this is where we start looking at our SEM micrographs. So in this slide, our first row shows you the original sample without any treatment. The second row shows you images of the magnesium oxysulfate cement stabilized samples. And then the third row shows you the EDS determined elemental composition that corresponds to the little tiny black star that you see on each of these images. And so the first thing we notice is if you look at just the shape, just the morphology of these particles compared to the original sample looks like what you'd expect of a basalt. A basalt is basically a rock that's been crushed out, and there's a lot of glass in it. So there's a lot of like sharp edges. It looks like basically shards of glass. And when we put it with magnesium oxysulfate cement, we saw that our shapes are now more indistinct. So there has definitely been some form of either erosion that happened because of the cement, or there's probably been more accumulation of these oxysulfate cement particles on the surfaces of our simulant particles. So when you look at the MMS sample, which is the first column, we see that there's some accumulation of more platey structures, and I'll show you another slide which zooms in on this image. So we saw more like platey structures, sheets-like structures being assimilated on the surface. Whereas for the MLS sample, we saw more, and the lunar samples, we saw more needle-like structures. These needle-like structures were very, very prominent in the GSC 1A lunar sample, which is the last column. And as for the GSC Mars 1, which was a volcanic ash, when you look at the original sample, you see this fluffy, very porous sort of particle, which is quite typical of volcanic ash. And we see a complete transformation when we put magnesium oxysulfate cement in it, where we saw now more sheet-like structures that have been compressed one on top of the other. And so we wanted to investigate what the composition of all of these were. When we look at composition at the first glance, you can see that, okay, magnesium sulfate seems to be consistently present in all the samples that we've looked at after the treatment. And then what we noticed, another thing that I noticed was that in the Mars samples, every time we see these platey sheet-like structures, we see more association of the magnesium sulfate with aluminum and silica, whereas in the lunar samples, when we see these needle-like structures, the association is mostly with iron. So definitely we are seeing some evidence of chemical reactions. So when we looked at it closer, so now these are all zoomed in of the same images that we looked at earlier. The first one shows you here the A, which is the JSC Mars 1 sample. These show you sheets of the JSC Mars, which was before this porous, fluffy looking structure. And now you can see that it is mostly composed, the main structure is mostly composed of the basic elements for the simulant, which is aluminum, silica, calcium, titanium, and iron. And between them, when we looked at these odd looking sheet-like structures, then we see more of the magnesium sulfate coming in. So we suspect that this is how the physical entrapment of mechanism works of MOC. So basically when it interacts with consolidated aluminosilicates, it is then binding them as acting as a binding agent between these sheets, keeping them intact. So we wanted to then look at the actual crystalline phases of the MOC itself. So in image B, the first one, where it says MMS, you see more of these platey structures. And these platey structures, through literature, we found out correspond to the 318 phase. And the other one, which is the MLS, which is the lunar simulant, shows more needle-like structures. you can see that the needle-like structures are much more well incorporated with the sample, and that it corresponds to literature. We found out that these needle-like structures are more of the 5-1 end phases. So this is where we find out, okay, why were we seeing that huge difference in compressive strength between the Mars and the lunar samples? So the lunar samples are dominated by the 5-1 end phases. These phases form needle-like structures. So you're talking about a higher surface area. The needles are better and well incorporated in the consolidated sample compared to a platy sheet. And so they do a much better job of just reducing the overall porosity of your sample once it's cured. And our third hypothesis is that the Martian and lunar simulants that are stabilized with MOC can provide a suitable extraterrestrial construction material. Now for this, I brought in some little prototypes here as well. We had to come up with something that was really out of the box in order to apply it. And for that, I've put in a little video for you. And so we tested our simulant for 3D printing. Basically, we wanted to modify our composite so it is viable to be pushed through a robotic arm in order to construct. And so we've made several different designs. These are hard to do. We usually, like Dr. Schwab said, this is a completely interdisciplinary thing. So I create the material, give it to the architect creates the design, comes up with a code, and then we both work together in order to come up with the final product. So this is just the beginning. Because we had limited amount of material, we didn't get a chance to do as many tests as we would like. But if you have good preliminary data, then this is just basically a start to a much larger future research. Whoa. So in conclusion, basically we decided to go with the magnesium cements because there are multiple sources for the primary reactants that go into a magnesium cement system. There's significant increase in the shear strength of all our magnesium treated simulants. Basically, when we looked at mechanism, when we tried to investigate, we think that it works through both physical entrapment as well as chemical reactions. And we believe that the chemical reactions are probably mostly between the amorphous iron and silica phases that are present in the simulant samples and the reactive species in the magnesium oxide itself. So applications in terms of extraterrestrial setting can be both. Yes, the robotic arm and 3D printing seems really, really cool. But honestly, if it were up to me, I would just make molds and create bricks. And that's exactly what I did. I used a silica mold to create these bricks with the magnesium sulfate cement. And the mortar is our own proprietary mix. And so, so there's plenty of options, but I think the idea is to have an open mind, and sometimes looking back is the best way to start something new. And with that, I'd like to thank Texas A&M's X Grant program for funding part of my research. I'd like to thank Dr. Schwab for being the best mentor I could have ever imagined. I'd like to thank my friend Javier for being with me, and my committee for being very, very supportive despite some very out-of-the-box research concepts that they've had to endure. And yeah, I'm open to questions.
Who's got questions?
Great presentation. My one question for you is, so the bricks that you made with the magnesium sulfate, was it, or whatever, do those have any different properties in like terms of weight? Are they like lighter or denser, or the same as typical bricks that we make?
I would suspect they're lighter because the magnesium oxide cement reaction is not just one thing I sort of missed to mention. It is a highly exothermic reaction. When I mix these samples, they usually get warm to touch while I'm mixing them. And there's a lot of research that's been going on in order to control how fast the reaction occurs. So that's why it's very viable for 3D printing, because it can cure as you're printing. So you're not waiting days before each layer of sample that you're adding. So yeah, because it's more reactive, you'd expect more bubbles to form, and I think it is generally more porous, so it is lighter.
Other questions? Oh, I'll go for the close one first.
Just really curiosity, is just any indication or thinking about if gravity will play a role in the structure itself?
Right. So actually, that's probably one of the only things that's in our favor. So on Mars, we're talking about a third gravity of Earth, and on the lunar surface, we're talking about a sixth. So when you think about it, low gravity means you don't need your material to be as strong as concrete in order to endure weight. So yeah, that's why we're not comparing it with concrete per se.
I was just wondering if you considered anything other than your manganese or magnesium.
Yes,
as a
it was a
possible-
process. It was a process. The mortar, the proprietary formula was one of them. We tested several different binders. I did some really crude ones, which included sodium silicate glass, precipitate with ammonium hydroxide, which was nasty reaction. But we went through several binders before, and honestly, it was a lot of like, hey, we tested this, it works. What do you guys think at NASA? And they're like, yeah, no. And then we kept doing that same thing over and over. I presented to them like several times till they were like, okay, this is actually kind of viable.
So I know you were really limited in like material. Did you ever think about doing like a fatigue test, so cyclical loading of the material, or like a hardness test of the material?
Right, so we tested it for compressive strength because it is the most widely used, and it does give me a lot more data points to compare it to in terms of literature. But yeah, so it depends on the application, right? So to begin with, I don't think we're thinking of constructing something like a skyscraper, but right now we're working towards a safe landing pad, a horizontal construction that would avoid dust plumes when a rover lands. That in itself, because I don't know if you guys noticed when Perseverance first landed, they couldn't do anything because the rover was completely covered in dust. And so there was a lot of panic-stricken ideas about how to remove dust. So if we have a proper landing site, it doesn't need to bear load, but that's a start. So that's where we're taking small steps at a time.
Other questions?
One comment. So for all of those experiments, you need water. How do you get water on Mars?
So water, surprisingly, this is a tricky question. There's been a lot of hypotheses about what happened to the water on Mars. And one that I really like, and a lot of people that I've talked to agree with, is that a lot of water that was initially on the surface is now trapped in the minerals. At really, really cold temperatures, you'd be surprised that the relative humidity on top of a sulfate salt that has 10 hydration, the humidity is about 75%. So even though the outer atmosphere might seem really, really dry, there has been several studies about how they can take water, sustain it in the poles, how they can keep the humidity on the surface so that the water doesn't sublimate out. So out of my research area, but there's been some progress in the water aspect.
All right. Thank you.
So, yeah, I have a question. Along the same lines, how much chemicals you need to make, let's say, a ton of cement? Like, is it too much, like acidification? Like you want to use acid digestion or carbonation and all this? Like, is it like too much material required to make a ton of cement, or can you find all that over there? Or
Can you repeat?
Sorry, could you?
Yeah, what kind of raw materials are required? I'm not familiar with the reaction. So to make a ton of, let's say, magnesium-based cement, how much acid digestion or what kind of acid you need, and is it too much to carry, or where do you find those kind of chemicals? It's very fascinating and innovative. So I'm just curious, you know.
Right. So you're probably correct. I personally did not look at the actual reaction to synthesize magnesium oxide, but there have been several papers that looked into that. Honestly, the idea is to try and find reactive magnesia itself, if possible. And a lot of the times, the synthesis of it in the surface will probably be more of a design, and probably it'll be a catalytic reaction, if anything. So I feel like that's sort of out of my scope. I'm sorry, I couldn't give you a better answer.
Oh, no worries. Thank you. It's very fascinating.
Thank you very much.